Hello and happy Friday. I'm sorry I couldn't be in class today, but I have some quick notes for you guys about counting trees and slot method in probability, and it's going to be a fun little math party. So a couple definitions for you right off the bat. Sample space is the set of all possible outcomes in a given situation. So what the heck does that mean? That means, for example, if I said, I'm going to flip a coin, what's the sample space here? It's all the possible outcomes. Well, when you flip a coin, what are the possible outcomes? You either are going to get heads or tails. Okay, so those are your possible outcomes. That's a sample space. In order to organize some data, sometimes we use tree diagrams. Okay, so that's really just a way for you to organize a bunch of experiments over and over again. Sometimes it can get confusing, so we use tree diagrams to help us there. And then lastly, independent versus dependent events. So an independent event doesn't affect one trial to the next. So for example, if I flip a coin and I get tails, that has no effect on my next flip. It doesn't matter that I got tails the first time. I still have an equal chance of getting heads or tails the second time. The other way to, dependent events, okay, are quite the opposite. So they do affect each other. So for example, if I have a deck of cards, and I draw two cards, and my first draw was an ace. And the probability of getting an ace again is going to be different, okay, because one of the aces is already gone. Actually, the probability of getting any card after that is going to be different because one of the cards is out of the deck. So those are dependent events. They do affect each other. And those are our definitions for this section. They're all written out for you, which is super nice, okay? So now I'm going to do our first example, one of my favorite problems in probability, and it's drawing a counting tree and list the possibilities for 3 coin tosses. So fun. All right, I like to organize it this way. We have 3 flips, so I'm going to write down, here's my first flip. Guys, what are my possible outcomes on my first flip? Well, either heads or tails. So there's 2 possible outcomes for one flip. But then I flip again. Now, let's say on the first flip I got heads. So then my second flip, again, I'm either going to get heads or tails. But let's say I actually got tails the first time. Again, I'm either going to get heads or tails on the second flip. So the moral of the story is that for every possibility, you want to branch another 2 outcomes for each flip. So from each previous possibility, you branch a new heads or tails. So the third flip, from this possibility, heads or tails. From this possibility, heads or tails. This possibility, heads or tails. Last one, heads or tails. So there's my tree diagram. That's what the first question is asking. Just draw your tree diagram. And that's a beautiful one if you ask me. Now, question A says, how many possible outcomes are there? List them all. So what do they mean by that? Here's what they mean. They mean if I flip a coin 3 times, I could get 3 heads in a row. Heads, heads, heads. So there's a possible outcome. So all I'm really doing is tracing down my tree diagram. Or I could get heads, heads, tails. So I'm just following all of these little branches. I could get HTH, heads, tails, heads. I could get HTT, heads, tails, tails. Or I could go to my next little tree branch, and I can get tails, heads, heads. THT, TTH, or TTT. Okay, so how many were there? I just listed them all, so that's part A. There's 8 possible outcomes. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Awesome. So now based on that answer, what's the probability that the outcome is all heads? All right, guys, take a look at these possible outcomes. There is only one that is HHH. So 1 out of a total of 8 possibilities will I get 3 heads in a row. It's kind of a small probability there. Okay, what's the probability that there are exactly 2 heads? Well, let's see. Exactly, oh, I'm sorry, I read that wrong. 2 tails. Okay, exactly 2 tails. Here's one that has exactly 2. This one has exactly 2. And this one. Now, this last one, it has 2, but not exactly 2. It has more than 2. So the ones that have exactly 2, there's 3 of them. So 3 out of 8 is my probability. And last one but not least, what is the probability that at least 2 are tails? Well, at least 2 is different than exactly 2. There's 2 here, 2 here, 2 here, and there are at least 2 in this last one. So this time we can include the tails, 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 making that 4 out of 8 for my probability, which is actually 1/2. So there is a 50% chance that I am going to get at least 2 tails. Kind of fun to do these problems, I think. So there's our first page of notes, and let's move on. Okay, guys, so number 2 says you're given a circular spinner with 3 equal sections, and it's labeled A, B, and C. So draw the spinner. So I drew that spinner already, 3 equal sections labeled A, B, C. And then it says draw a tree diagram that shows the possibilities when the spinner is spun twice. No problem. We are now tree diagram experts. Okay, so first spin. Possibilities are A, B, or C. These are independent events because my second spin really doesn't matter what I got on the first spin. There's no effect. So my second spin is either A, B, or C. And again, we just branch from each previous possibility. So there it is. There's my tree diagram, and how many outcomes are there? List them all. Okay. Again, we're experts. We got A, B. Oops. I'm just following A, each little branch. So A, B, A, C. Or I can have BA, and then BB, and then BC. Or CA, CB, or CC. So how many outcomes are there total? There are 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the probability that 2 spins will contain at least 1 A? All right, we need at least 1 A. At least 1, okay? This one has at least 1, this one, this one, this one, and this one. So how many is that? 1, 2, 3, 4, 5 out of 9 total possibilities. What is the probability that 2 spins will contain exactly 2 B's? It doesn't say at least, so that's exactly 2. Let's do this one in orange, exactly 2 B's. So let's see. Well, guys, there's only one that has exactly 2 B's. So 1 out of 9. What is the probability that 2 spins will not contain a C? So which ones have no C's? Okay, so here's 1, 2. That one does 3, 4, and that's it. 4 out of 9. And what is the probability 2 spins will contain only 1 B? So that only has 1 B. That one only has one B, one B, one B. 4 out of 9. Very nice. So there's another tree diagram example. So fun. Last part, let's move on. So this last part is actually a counting principle, and in order to count like high numbers or high different combinations almost really fast is to use something called the slot method. Okay, so the slot method is just a basic counting principle. We're going to go over it today. If one event can be chosen in P ways and another independent event can be chosen in Q ways, then the events concur in P times Q possible ways. Whoa, super confusing. I'm going to explain that second bullet point as we do problems. So how many different ways can you buy a lunch from the school's cafeteria if there are 5 sandwiches, 3 salads, 4 chips, and 5 drinks? So I'm saying, like, what are the different types of almost like combinations that we could have? Like I pick a turkey sandwich, a Caesar salad, barbecue chips, and a soda versus the ham sandwich and a garden salad with plain chips and water. You know, so like how many different combinations can I make of these? Well, let's see. This is the second bullet point. Basically, it's saying if there's all these different options, all I need to do is multiply those numbers together, and that's the amount of different ways I have. So I'm choosing one sandwich, and there's 5 possibilities. So there's 5 sandwiches, that's 1, times the 3 salads, the 4 chips, so I'm just multiplying. 5 times 3 times 4 times my 5 drinks. So there's 4 different items to choose from, and all I do is just write down the number of options there are, multiply those numbers all together. So 5 times 3 times 4 times 5 is 300 different combinations or different lunches that I can actually make. So there's no way I'm going to make a tree diagram and say if I pick the first sandwich and then, you know, that's going to be insane. I would have 300 different choices. This is a faster way to count, okay? So Holly has 4 shirts. Holly's my mom's name. That's fun. Holly has 4 shirts, 2 pairs of jeans, and 3 pairs of shoes. How many different outfits can she make? This is a great question if you're packing for like a Europe trip or something and you're like, okay, I only have a small suitcase. How many different outfits can I make with these 4 shirts, these 2 jeans, and these 3 pairs of shoes? Let's take a look. Hopefully everything matches. We got 4 shirts times 2 pairs of jeans times 3 pairs of shoes. That's 24 outfits. Not bad. That'll last you a month. Well, kind of, if you repeat a couple times. Fun. Last one, and this is possibly one of my favorites. 6 students are racing each other. So here's where the slot method comes in. To see who will be starting at a track meet, how many ways can they come in first, second, and third? So this one's a little bit different. So we're looking for 3 different places. So we have first place, we got second place, third place. So guys, how many different people could possibly come into first place? How many options are there? Well, there's 6 students, so there's 6 possible people that can come into first. Okay, seems fair enough. How many people could come into second? If you're thinking 6, you're close. But don't forget, someone already came in first place. So how many people are left over to come into second place? 5 people. For the same reason, now I already have someone in first, and I already have someone in second, so there's still 4 people left to possibly come into third. So this problem, and that's why we call it the slot method. We kind of drew out 3 slots, and we fill in the numbers. So this is 6 times 5 times 4, and that's 120. So there's 120 different ways that we can get a first, second, and third place winner. What does that mean? It means like I could come into first, Jasmine could come into second, and Heidi comes into third. Or it could be like then B comes into first, Shane gets second. You know what I mean? Like there's a whole bunch of different options. 7th period, sorry, I left you out. Whatever. Okay, so that's it, guys. those are our notes for today. And that's it. Have a good weekend. Miss ya. Bye.